Hey guys, and welcome to a new video in this computer vision tutorial here. And today we're going to talk about geometric transformations and like what they can be used for. And I'm going to show you some different kind of examples of like transformations that we can do on images. And then I'll also show you like how we can do it in OpenCV with some code examples. So I've been really excited to show you this video here because there's so many cool things that you can do with geometric transformations in computer vision to like pre-process an image and do some other different kind of stuff. We can have like, for example, we have like a perspective transformation where we can like have an image where we're looking in front of like a snooker table, and then we're making a perspective transformation so we see like the picture from above instead of like from the front. And there's also some other different kind of transformations that we're going over in this video that can be used for many important practical stuff. So first of all, we need to talk about like geometric transformations and what they are, because we have some different kind of geometric transformations where we just have like the original geometric, which I'm going to show you some different couple of like examples of. And then we also have some pixel coordinate geometric like transformations and some brightness interpolation, which we have in the end of the slide here. And then like the applications of geometric transformation, like if we take the example over here to the right, we can see that we have an image here with like a bookshelf or like some paper shelf that is like a bit screwed here. Like it's not like all the lines are not like parallel to like the first line here, so it's a bit distorted our image here. But then we can apply some geometric transformation that can like make our picture here like more like squares, and like the lines will be more even and like totally parallel to each other, so like it's easier to do image processing or image analysis on the image here to the right compared to the left one here. And this is just done by using some different kind of transformations that we're also going to see an example on with a number plate on a car. And we can just use them for like computer graphics, or we can use them for distortion. Like we can introduce distortion to an image, or we can eliminate a distortion from an image. Let's say we have like an image that is distorted, like let's say we have a fisheye lens on our camera, then we have like some distortion where like our image in the boundaries will be distorted, like or like rounded, and then we can like eliminate that distortion with some different kind of transformations that I'm going to show you in the end of the slide here as well. We can also like just like image processing, pre-processing, and text recognition when we have done our pre-processing with our transformations, and then we can like recognize signs and numbers and etc. So then we need to like formulate the problem that we're facing with our image that we want to do some transformation on. And first of all, we have our distorted image here, which is just like an image with the pixels here, and then we can have like the corrected image here on this form here, which is like the image over here to the right. This will be our distorted image, and then we do some transformation on the image here, and then we will have our corrected image here. And so like map between these two images here, like we can have this formula here where we take like it's just like the transformation of the corrected image here, like of the corrected image here is the same as like the distorted image here, and then we can take the inverse transformation to like map between the different images. So we also need to like define the transformation that we're going to use, and we can either like know in advance like the transformation that we're going to apply, or we can like determine our transformation through correspondence, which I'm going to show you in the end of the video here, where we're going to have a picture where we're going to like determine our correspondence, like or points in the image that we want to do something with. And then we also like need to like know the image and like image to image transformation. So, and then in the end, when we have defined our transformation that we want to apply, we then need to apply that defined transformation to our image, and then we just apply it for like every point in the output image, and we determine where it came from using the t from mapping, like up here, and then we can interpolate a value for the output point, which we have like some different kind of methods for that I'm also going to show you in the slides here. So we have different kind of transformations, and the ones we're going to focus on in this video is the linear transformations in three-dimensional space, where we can have these like affine transformation and the Euclidean transformation, where we have 6 degrees of freedom, which means that we have 3 degrees for translation, and we have 3 degrees for rotating. So we can translate in each direction, like on all the three axes in the three-dimensional space, so X, Y, and Z. We can translate on those axes, and then we can rotate on all of those axes as well. So we can have like some different kind of transformations with our linear transformations in 3D, where we can have like no change, or we can like translate here. We can see that we translate in the Y and X direction, and then this will be our transformation matrix. So depending on what type of like transformation we want, we get some transformation matrix, and this is the transformation matrix that we're going to apply to our image. And if we don't really know like our transformation beforehand, we can place some points and we can get this transformation matrix from that. So we can also like shear in different kind of directions, where we like kind of like stretching our image, or we can reflect our image or object around some of like all of the axes and stuff like that. So we can do a lot of different kind of things with transformations here and our images. And we can also have like some higher order transformation, like the parameterized and freeform transformations. But in this video, we're going to focus on the linear transformations and do some practical examples of that. So one of the transformations that we're going to focus on here is the affine transformation, where we can have like this known transformation where we can translate, rotate, etc. Where we have like our transformation matrix over here that we then can apply to our image here, like our output image here, and then we will translate that image, and it will then create a new image that is translated to compare to like the input image. We can also have this unknown transformation that I talked about, which will require at least 3 observations. So if we're given an image and we don't know the transformation, like we will have to like go into that image and tell our algorithm or function that like give our algorithm a function like 3 observations. It could be like 3 points that we want to do something with, if we have like triangles in our image, or also we could have like, if we have a square that we want to do, or a rectangle we want to do something with, we could give our function or algorithm like 3 points of that, like 4 points of that rectangle, and then it would use that as a transformation to apply to the image. So like it could be points in an image like coordinates of objects and stuff like that, and then it will find, like we can use this a function in OpenCV that will find like the coefficients here for this like transformation matrix here, and then we can apply that transformation matrix to our image. So we do this here down here in OpenCV, where we first need to like have our affine matrix, or like our affine transformation matrix, which is this matrix up here, and then we need to give it the points that we want, like that we want to apply to our affine matrix. And then we have this warp affine here, which is doing the actual transformation of the image, where we first give it the input image and the output image, where we want to like store the translated image, or like the transformed image, and then we give it the affine matrix here, which is the matrix up here with all the coefficients that we want to apply to our image. So an example of a simple affine transformation is like this car number plate here, and I'm going to show you this example here in code, where first of all, down here in the first example, we have this image here, where we can see that it is not like aligned in the image, and it's pretty like hard for a computer, or it is an optimal way for a computer to like read the numbers or letters in the car number plate here. So let's say we're building like some application or like some practical program where we're going to like let's say we're going over a bridge, for example, and we need to like tell all the cars going over the bridge, so that we can just scan the number plates. And you've probably like seen this before in the real world, where like it's like pay by plate. So you pay with your number plate, and it just takes a picture of it and do some analysis on the plate, and then you will get billed from your number plate. So first of all, we're rotating the image here to like get it more aligned in the picture, like, or like more like so it's like a box instead of this, like it's kind of like screwed here, and it's not really aligned and not really easy to read for a computer. And then we can scale our image if we want to do that, if it's not big enough, or like we just need a bigger image to like read the letters and characters inside of the number plate. And then in the end here, we can use this like skewing or shearing the image, where we are actually like applying the affine transformation that we have the transformation that we want to apply to our image. And this could be like, for example, that we gave them like 4 or 3 points here in the image, and then it like tried to align the number plate here, so we'll get a good fine rectangle here that we can then do an image analysis on with like 90 degrees here in the corners. So we can also have like the unknown affine transformation here, which is like just a continuation from the last example on the previous slide, where we can have like some observations that we give to the algorithm of function, and we need at least 3. So we could give like three points here in the image, or we can give like more points. And then this unknown affine transformation uses this pseudo inverse for like the unknown transformation. If we have like the known transformation where we already know like the transformation, we can just use the original inverse of our matrix or of our transformation matrix. So in OpenCV here, it takes like these 3 source, like it could be points in the image, like the 3 source points here, and then the 3 destination point where we want to transform our source points to. So let's say we took like 3 points here. I'm going to show an example of it in OpenCV as well. Let's say we took a point here and here and here, and then we want to store like the points like around here and here and here, and then it will actually like output this image here, where like we get a fine and good like 90 degrees rectangle here in all the corners. So like this is how we can use like an affine transformation in OpenCV, and also like just in computer vision in general, and it's a really practical and useful thing to know, and also like be able to do, because it just makes image analysis and much easier, and also like just pre-processing images, it can like get really huge benefits in the end. So we can also, like I talked about this perspective transformation here, where we have like some kind of like taking a perspective of that image here, which we're going to show an example of with a snooker table. So we just like do some perspective projection, where we just like we see the image from above, like, or in an eagle or bird view, and we have this planar surface here that is like it's not parallel to the image plane. So when we do this perspective projection, we won't get like it is not parallel to the image plane, and then we can like just perspect that transformation and get like a perspective image of the actual image, and it can't be corrected with the affine trans, and therefore we need like to do this perspective transformation, because we can like make a bird view from an affine transformation. And like this is the affine transformation that we've talked about in the previous slides down here, where we have these A coefficients, and when we're talking about perspective transformations, we have this transformation matrix down here, where we're applying this weight here to our image pixels, or like image coordinates as well, to like do this perspective transformation instead of just doing our affine transformation. So if we want to do this perspective transformation in OpenCV, and I'm going to show you like kind of exact this example here, and how we can do it in actual C++ code in Visual Studio. So here in this case here, we give them 4 source pixels, or like coordinates in our image here, and then we have like this destination coordinates that we want to like transform our image to, and then we can calculate this perspective matrix here in OpenCV with this built-in function here, get perspective transformation, and that function just takes like the source points and the destination points, and then it gives us this matrix here, the P matrix here with all the coefficients that we need to do the perspective transformation. And then we can use this warp perspective here, which is like kind of the same method as the like warp affine. It's a built-in method that we just like apply our perspective matrix to the image. So it just takes like the original image and the resulting image where we want to like store a transformation in, and then it takes the perspective matrix here and the size of the resulting image. So this is like the matrix, the perspective matrix that we want to apply to this result, the result image or matrix here. We can also in OpenCV, like there just like short introduction, we can have like rectifying homographies, where like we have an image transformation that can be computed such that like the scan lines in an image can be directly matched on images. So here on the top here, we can see that we have some buildings here that is like rotated, and images that is taken from different kind of places. And we can see down here that when we're like applying like our rectifying homographies, we get these lines here, like or scan lines that can be used for a lot of different kind of things, like scanners, or if we just want to like find lines like or matching objects in an image, like we can use these lines here where you can see like the line here goes perfect through like the roof here, and it's like kind of the same here. And also like this line here just goes like through like the bottom of the build, like the first floor here, and perfect also on the last image here. So it can be used for a lot of different kind of things, and they would just like to give you an introduction to like what it can be used for. So the last thing we're going to talk about here in the slides before we're jumping into Visual Studio, and I'm going to show you some actual practical examples, is brightness interpolations. And it is like when we have locations that are not like integer coordinates, then we can like interpolate our output pixel value from the nearest pixel in the original image. And there are different kind of like methods to do that interpolation, and most simple one is the one-dimensional nearest neighbor, where we just like go to the nearest neighbor in like the points. So like these yellow and green here, it could be like it is pixel coordinates in our image, like our pixels in our image. And then we want to go like from these neighbors here, like from these neighbors here to this neighbor up here. And when we're using the nearest neighbor here, we just go like in this like square line here, where we just go like from like this. So it's not really like that smooth and a transition from like the neighbors and going from neighbor to neighbor, where we can then apply like another interpolation method called like bilinear interpolation, where we have like 2 points here, and then we just go in a straight line from each neighbor to neighbor. So it's a bit more smoother to do this, and like we can like find the points here between these two image like pixels here. So like probably like best one and most used one when we're talking about like image like interpolation, when we're interpolating brightnesses in an image, it is like probably like the bicubic interpolation, where we have like some other like curve like or polynomial, where we want to find like the coefficients for them. So in this case here we have like 2 pixel coordinates again, and we try to like, it is based on finding the gradients. So like we have like, for example, let's say we have a gradient here and a gradient here, like for the points that this curve is fitting, and we have like a gradient up here, and then it's just like trying to fit these gradients here so we get like a more smoother surface. And we will also like see this like down here, we get like a more smoother transition when we're interpolating our brightnesses in an image. So if you want to like hear more about like brightness interpolation, because it can be used for a lot of different kind of things, and there's like a lot more about it. So if you want me to go more in depth with it, like comment down in the comment section if you want to like hear more about this, because it can be used for a lot of different kind of things. And if you have like done any image analysis before, like there's a lot of like options in some like Adobe Photoshop or something like that, like where you can choose like between like if you want like a bicubic interpolation method or bilinear and stuff like that. So most of the time we will just use this bicubic like interpolation method, because it gets more it's more smoother, and also looks like it also like looks at the 16th like nearest neighbors, where it like looks ahead of it, so it like calculates the gradients for like the pixels ahead of it, and then it gets like this smoother curve here for our interpolation. So we can actually apply this brightness interpolation in OpenCV, where first of all we just need to like define our interpolation scheme, and we can just there's built-in functions here for OpenCV where we can use like inter-nearest, interlinear, or inter-cubic, and then we just use these transformation matrices, as we did on previous slides with some of the examples, where we have like this warp affine here, where we give the parameters here that we saw in the other slides. And then on the last parameter here, we just give it the brightness interpolation method that we want, and we can do the same for our warp perspective down here, where we just again apply the interpolation method that we want to apply to our perspective transformation in the last parameter here. So we can also have like distortion when we're talking about like distortion on our camera models. We can have like radial distortion, and it is like radially symmetric from the optical point, which is like around here, and then it's like a change in magnification. So one of the examples of distortion on the camera model is like a barrel distortion and penetration distortion, and they're often like caused by the lenses. Like let's say like this could be like some kind of like fisheye lens here, and we have this barrel distortion here where we can see like the lines they're not parallel and they're like stretched out and rounded in the corners here, and the same here, which is like kind of the opposite of the barrel distortion, like the pin fusion distortion. So there's different kind of like distortion on our images, and we can also have this tangential distortion, which is an uneven magnification from one side to the other, and we can see that the lenses are not parallel to the image plane. So down here we can see that we have the tangential distortion here because our camera sensor is not parallel to like the image plane here. So that can like cause some distortion as well that we need to like take care of. But these type of like distortions, they can be eliminated or removed from our camera models by like calibrating. Like when we're going to use our camera, we first need to like calibrate our camera, and we can do it with like different kind of methods. We can either use like multiple images or like calibrate with known objects in an image, and then change positions and then calibrate our camera from that. And then we can compute the camera matrix and our distortion parameters, and then we have built-in functions in OpenCV where we can use where we can remove the distortion from our image using the distortion parameters we find from calibrating our camera. So this could be like an example over here to the right, where we have like this chest plate here, where these line here, and then we find like the corners of all like the squares here, and then we can calibrate our camera from these objects or like these different kind of images. And then we have like OpenCV here, where we can calibrate our camera here, where we just give it like all the points that we have found from our calibration of the camera, where we have like the camera matrix, the distortion coefficients, rotating vectors, translation vectors, and stuff like that. And then we can just use the function here undistort, where it just takes like our camera and then the corrected image, and then like the distortion coefficients, and also like the camera matrix that we found by calibrating our camera, and then we can undistort our image. So let's say we have a camera model that has this barrel distortion here, then we can do our camera calibration here with some different kind of methods, and then we can just undistort our image, and we'll get a more smoother and more like undistorted image compared to this barrel distortion here, which could cause problems to our image analysis and image like processing in the end. So let's jump into Visual Studio. I'm going to show you some different kind of examples, like how to use some of these methods in OpenCV and C++. So we're going to jump into the Visual Studio here, and I'm going to show you like the different kind of examples with an affine transformation of the number plate of a car. And then we're also going to do this perspective transformation of a snooker table that we see from the front, and then we make a perspective transformation, so we kind of like see the image from above as like in a bird view or like eagle view. So first of all, here we're going to like read in the images just that we're going to use for our transformations, and then we just check if like we fail to read in the images, and then it will throw an error. So first of all, we need to like find the point in our image where we want to do, because this is an unknown transformation that we're going to do. So we need, like as I talked about in slides, we need to give our transformation matrix or like the functions some like corresponded or some points that where we want to apply our transformation to. So first of all, we're just going to find the points in our images with the mouse here. So when I open up the images here, I have to click at the points that I want to use for my transformation matrix, and then it will then pass those pixels to the function and do the calculations, and then output and then show the output on the images again. So if we go down here where we do the actual transformations, then we'll get like the points from the plate, and also like destination points where we want to have our plate number, or like our number plate. And then we calculate this affine matrix here that we're then going to apply in our warp affine function down here. And then we just apply that transformation to the image, like the plate image here, and then we just output the plate transformation down here with this imshow command. So another example we're going to do is like the snooker table, where we're going to use this perspective transformation. So to get the perspective transformation matrix, we just use this function here, get perspective transform. And again, we just find the points in the image where with the mouse here, and then it just passes those like points to the function here, and then it calculates our perspective matrix, and then we can do the actual perspective transformation on our image with this warp perspective transformation function down here, and then output the image here. So if we just run the program here, we can see that we get up the images here that we want to find the points on. So if I just click with the mouse here at the points where I want to get the points that we can use for our transformation matrix, I'll just take the points here on the number plate. So we take 3 points in this case here when we're doing the warp, like the affine transformation here, because we only need 3 points. And then I need to give give the function the destination point. So I want to like get the number plate like over here. And then we need to do the same here for original, like our snooker table here, where I just give them the points of the corners here of the table, and then the points where I want to like have the destination of our image. So it is like around up here, because we want this perspective transformation. And now when I hit escape here, it will do the actual calculations and show the output image. And we can see down here to the right, we have like the transformation of the plate here, and we can see that this image is much easier to read compared to this image over here, if we were going to do some like number plate recognition or something like that. And these were just like arbitrary points that I chose in the images. Like you can calibrate this more, and it was just like with the mouse I just went in and clicked on the points that I want to take. And we also did this perspective transformation here with the snooker table, where on the image here to the left we're seeing the snooker table like from the front. And then we want to do this perspective transformation, where we like transform into a perspective where we get this eagle or like bird view over the table here. So this looks like kind of like an image taken like from above the table, where like the actual image is taken from the front. So this can be used for a lot of different kind of like practical applications, and this is only done by doing like these 2 lines of code with the built-in function, and then we give the functions the different kind of points that it needs, and then it just uses math and some different kind of algorithms to do these transformations, and it can be used for a lot of different kind of practical examples. So it's a cool, pretty cool feature. I'll say, like we get like pretty good transformations here, and for a number plate, like it's easier to do some calculations, and also like we just get what we want to focus on, and we can use this for image pre-processing before we're doing some image analysis. Like on the snooker table here, it can be like, for example, we want to like calculate the distance between the balls here in the image, and it's probably easier to do it on this image than compared to like this image, or we want to see like get a better understanding like what's here on the back. So it can be used for a lot of different kind of things, and in this video we've been over like the different kind of transformations that we can use in OpenCV. Like we've been focusing on the linear transformations, and also like the brightness, interpolation, and distortion on cameras. Like let's say we have like a fisheye lens, and we want to remove that distortion from our camera before doing some actual calculations. Like it's also possible to do that in OpenCV. So those are pretty nice and cool features for doing some image pre-processing, and it's also like very useful. So we just like only get the information we want in our image, and we just like crop out all the stuff we don't need in an image, like for example like the background here and stuff like that, and we just take the original snooker table and we want a perspective of that table to do some analysis on. So thank you guys for watching this video, and remember to hit the subscribe button and bell notification under the video, and also like this video if you like the content and you want more of it in the future. I'm currently also doing this algorithms and data structures tutorial and an artificial intelligence tutorial, so if you're interested in one of those, I'll link to one of them up here, or else I'll just see you in the next video guys. Bye for now.